Okay, so now that we know about zeros of polynomials, we're going to use them to work backwards and construct a polynomial. And in this video, we're going to focus on polynomials that have rational zeros only. So we're not going to look at irrational zeros or imaginary or complex zeros. So let's get started. Let's determine a polynomial of lowest degree with rational coefficients. That just means you can't have any coefficients that have square roots or imaginary numbers in them. So determine a polynomial of lowest degree with rational coefficients whose zeros are, how about 2, -3, and +3? That'll be our first example. All right, so the part about being lowest degree, what we want to do here is we want to keep the multiplicities of these zeros as small as possible. So we're going to assume that each of these has a multiplicity of 1, and that's going to mean that we're going to have a degree of 3 for our final polynomial. So we know that our final answer, is going to be, it's going to be a cubic polynomial, okay? It's got to be. If it's smallest degree and it's got 3 zeros, then it's going to have degree 3. Because we're going to assume multiplicity of 1. That's the smallest that can be. So now, if 2 is a 0, then x minus 2 is a factor. So we're turning each 0 into a factor, and factors always multiply together. So if -3 is a 0, then x minus -3 is a factor. And finally, if 3 is a 0, then x minus 3 is a factor. And now we have to multiply all of the factors together to get our polynomial, to get our cubic polynomial in this case. And the only types of numbers we're dealing with here are rational. We don't have any complex numbers or square roots, irrational numbers. So this part about having rational coefficients, it's going to naturally happen anyway. We don't have to do anything special. The first thing I'm going to do is rewrite this second factor in a form that I like better, and I'll call it x plus 3. And now I've got to get down to multiplying the 3 factors. Now most students, the biggest thing they struggle with here is these problems are tedious. And so a lot of students want to try to multiply all 3 of these together all at once, and that's a bad idea. What I do recommend though, since you can't do them all at once, is anytime you have conjugate factors, multiply those together. So in this case, x plus 3 and x minus 3 are what we call conjugate factors. They're the same, except one has a plus, one has a minus. And if you do that, you're going to get x squared, and you're going to get minus 3x plus 3x. Those cancel out. Those are 0. Anytime you multiply conjugates and you do that inner product and that outer product like that, they're always going to cancel. So that's the beautiful thing about multiplying conjugates. And then all that is left is the minus 9. So when I multiplied those two guys together, I got x squared minus 9, but I can't forget about my x minus 2. I still have to multiply my x minus 2 by this x squared minus 9. And the way I'm going to do that is I can tell that my highest degree term is x cubed. So the way to get x cubed is x times x squared. So that's x cubed. And now I'm going to search for all the x squared terms. The only way I can get an x squared is to multiply this -2 by this x squared. So that's my only x squared term. And then I look for all my x terms. The only way I can get an x term is to multiply this x by this -9, giving me -9x. And last, all my constant terms. And the only way to do that is -2 times -9 to get plus 18. And so this polynomial is degree 3. If you factor it, it factors like this, and it has the zeros that were asked for. So this polynomial satisfies all the conditions in the problem. It's a matter of converting your zeros to factors and multiplying your factors together. And that's it, okay? So it's tedious, but not difficult to understand. Just take your time, get the arithmetic correct. All right, let's do, we'll do two more here. They sort of advance in difficulty as we go. So I'll abbreviate now. Let's assume rational coefficients. Again, we don't want any square roots or imaginary numbers in our answer. So let's assume rational coefficients. Let's again assume smallest degree. Okay. And let's also assume that in the final answer, the coefficient of x is 14. So this is an interesting little kink in the problem. And so now I'll give you the zeros. So let's say that -1 is a 0 with a multiplicity of 2 and 4 is a 0. Okay, I'm not telling you its multiplicity. However, if we want the smallest degree, then I'm going to assume that 4 has a multiplicity of 1. So now let's set up this problem. I've got -1 is a 0, which means that x minus -1 is a factor. And it's a multiplicity of 2, so I'm going to have it twice. 4 is a 0, so x minus 4 is a factor. And this is what we have. Now, x minus -1 is the same thing as x plus 1. So now let's back up for a second and sort of analyze this strange condition that we want the coefficient of x to be 14. When we multiply all of this out, we're going to get an x cubed polynomial, right? So you're going to have an x cubed term, an x squared, an x, and a constant. That x term needs to have a coefficient of 14. We can't figure that out right now. So we're going to multiply this out as if that condition wasn't a problem, and then we'll see how to adjust our final answer to make sure that we get it. All right, unfortunately, we do not have any conjugates in these three factors. X plus 1 and x plus 1 aren't conjugates because one is not a plus and the other a minus. They're both a plus. So we just have to multiply it all together. So I'm going to multiply x plus 1 times x plus 1. So I get my x squared term is x squared. Then I get a 1x and another 1x, which is 2x. And I get a 1 times a 1, which is 1. I need to carry down and still multiply by my x minus 4. So I'm going to get my x cubed terms, and the only way to do that is x squared times x. Then I'm going to do my x squared terms. I could do that with x squared times -4, so that's -4x squared, positive 2x squared. So -4x squared plus 2x squared is -2x squared. Now I'm going to collect all my x terms. So I could do that by taking 2x times -4, so that's -8x, plus 1x. So I've got -8x plus 1x, which is -7x. And last, I need to get all my constant terms together. The only way to get a constant term is to take 1 times -4, which is -4. Now, this would typically be our final answer, except we need this coefficient to be 14, okay? I can't just change it to a 14. What I need to do is, I can take and I can multiply this whole polynomial by any coefficient that I want. If I were to multiply this whole thing, let's take a look at it. If I were to multiply this whole thing by -2, that's going to change my -7 to positive 14. So let's write that out. -2 times x cubed minus 2x squared minus 7x minus 4 equals, distribute the -2, And now this polynomial has a coefficient of 14 on the x term, right? But if you were to factor this, that's the final answer, by the way, but if you were to factor this, look at how it would factor. It's going to be x plus 1 times x plus 1 times x minus 4, because that's what we started with. But it's going to have this leading coefficient of -2. And you can see that if you put a coefficient out here, it does not affect your zeros. They're all intact, right? All it does is affects the coefficients in the final polynomial. So you're allowed to adjust this coefficient. You can take a polynomial and multiply it by any coefficient that's not 0, and you'll still preserve the zeros of the polynomial. So that's how you take care of conditions like this where you want particular constraints on coefficients, okay? Let's do another example. Okay, so let's look at, now I want degree 5. I want integer coefficients. That means I can't have any fractions in my coefficients. So now I have to have whole number coefficients, plus or minus. I can't have fractions, I can't have square roots, and I can't have imaginary numbers. So that's going to be interesting. We'll have to deal with that. Integer coefficients, and we'll say that the zeros are 0, which has a multiplicity of 3, and 1/2, which has a multiplicity of 2. And so you can see here that we've already got our degree 5 taken care of because this is going to be degree 3, this is going to be degree 2, all together giving us degree 5. So if we were to set this up, we're going to build it now as 0 turns into a factor of x minus 0, and that has a multiplicity of 3. You could put an exponent of 3 on this and not copy it 3 times if you like. And then we have x minus 1/2 2 times. Okay? And we have to multiply all of this out. Now, you can see that if you multiplied this out because of these 1/2s, you're going to have some fractional coefficients. And we're not allowed to. We have to have integer coefficients. So what you could do is you could multiply all of this out like we did in the previous example. No problem with that. You just have to deal with the fractions. And then at the very end, you could multiply by a coefficient that would turn all of the fractions into whole numbers. Okay? So that is certainly a way to do this particular problem. But this one's a little different than the last problem. We're not trying to make any one coefficient a particular number. We just want them all not to be fractions. Okay? So what we can do here is we can sort of take care of that right at the beginning. So let me show you. X minus 0 times x minus 0 times x minus 0. That's just x to the 3rd power. Pretty simple, right? Now, x minus 1/2 times x minus 1/2. What I'm going to do is I'm going to build in, let's not write equals, okay? This was our starting point. What we're writing next is not equal to this. What we're going to do now is build in a coefficient here that's going to take care of this fraction and build in another coefficient here that's going to take care of this fraction. Let me show you what I mean. So I'm going to take x cubed times 2 times x minus 1/2. Right? The coefficient can be introduced at any point in the process of building your polynomial. You don't have to wait until the very end. In the last example, we had to, because we didn't know what that coefficient of x was going to be naturally. We had to figure it all out and then adjust it at the very end. Here, I just need to make sure this is not a fraction. The way to make it not a fraction is to multiply it by 2. And similarly, on the last factor, I'll multiply the last factor by 2 as well. Now, if this had a denominator of 3, I'd multiply by 3, right? Always multiply by whatever your denominator is, so it will cancel after you distribute. Now we've got it set up like we want. The first thing I'm going to do is I'm going to copy my x cubed times, and I'm going to multiply all of this together to get 2x minus 1 times, and I'll do the same thing here, 2x minus 1. Okay? So now I can see I don't have any fractions left, so I know I'm going to get integer coefficients. I know I'm going to get degree 5, so let's proceed to multiply. So you can multiply this in any order you want. You can take the x cubed times the 2x minus 1 first, get that result, and multiply by the 2x minus 1. Totally fine. We don't have any conjugates here, so we don't have that beautiful cancellation we talked about. What I'm going to do is multiply these guys together and save the easy part for the very end. Okay, so I'm just going to bring down my x cubed still, and I'm going to multiply all of this together. So I get 4x squared minus 2x minus another 2x. That's minus 4x. And then I get plus 1. Finally, you can see how easy it is now to multiply by my x cubed. I just distribute it. I get 4x to the 5th minus 4x to the 4th plus x to the 3rd. And so this is a degree 5 polynomial, integer coefficients with these zeros. Okay? So all the problems definitely had some similarities. They had the same underlying concept, but I wanted to introduce you to how to address issues that arise when you have certain constraints on your coefficients as well.